Elsewhere on my channel, you'll see a video entitled Plussing Up the Heathkit IP-18. This is not that power supply. This is another Heathkit IP-18, this time that I actually picked up for very, very, very little money. So I didn't know what to expect, but I thought it would be interesting to have a look and see if I could modify this one in some other way. And so this is what we're going to be doing. Externally, it looks quite well built. I've already removed the 6 self-tapping metal sheet metal screws that hold the cover on. And the good news is these were the original Heathkit screws because they're all identical and they're all slotted. So that's good, because if you get something vintage and all the case screws are there and they all look identical and they all look there, it means that if someone actually did go into a piece of equipment over the last half century, at least they took care to save all the screws, so they were probably careful into whatever they did. So without further ado, let's open this up and see what we're going to be doing to it. Here's the rear view with the original Heathkit 3-wire flat line cord, which is in very, very good condition, so that's always nice to see. Plus the Heathkit blue and white model and serial number label is in perfect shape. Again, this looks very promising. Let's have a look inside. It should go without saying that the 4 rubber feet, the original Heathkit feet, are gone. This is entirely always the case. They deteriorate, their adhesive falls apart. That's no problem. We have plenty of replacement feet, so we'll be taking care of that too. So let's open her up. And by the way, the case itself is in decent shape. A couple of nicks and scratches. I don't know, it's in good enough shape that I may just leave it alone. Or I may strip it and totally refinish it, as I've done with my IM103s. But we'll see. It looks good enough. So here's the inside. Let me reorient some light on the subject. And when I looked at this first, it appears to be very well built, at least per the Heathkit manual. So I didn't see there's no components missing. It does work. I actually tested it. So again, this is a 1 volt to 15 volt DC supply that's has current limiting up to 500 milliamps or half an amp. There's nothing looks untoward. It looks like someone might have recapped at least this guy already. This was not vintage. It's not modern. It's not modern, but it's not vintage either. This guy, this large electrolytic here, is the original 1970s vintage electrolytic. It's, I believe, 2500 mics at 50 volts or something. So I'll probably be recapping this guy, and I may recap all 4 capacitors on the PC board, as well as this little electrolytic here that's sort of off in the distance. So other things I'm thinking of doing, hopefully in this video, are this flying 1K resistor is in the schematic, but this is very un-Heathkit, I think, the way. This is how the manual tells you to do it. But I think we'll be adding maybe a little terminal strip here and just redoing this properly with a wire. I don't know what they were thinking here. Also, in the original design of this, all of the AC wiring, in other words, the line cord, goes straight into the PC board, the main PC board. And then other things come out of the PC board and get connected. For example, the AC power on neon indicator is soldered into the PC board on the back side here. So is, there's the power switch, the on-off switch is wired into the back side. And I would like to get all of the primary AC stuff off the circuit board and rebuild that off board, probably in this area here. So maybe put some sort of terminal strip. And by the way, there's no fuse. So this one was of early enough vintage that it was one of the ones that was shipped with no provision for fusing at all. In later incarnations of the kit, Heathkit actually had you have a flying fuse, I'll call it, a pigtail fuse just off the power switch. And it would just lie here with a piece of, a little fabric tube over it to try and prevent shorts. Here's the fuse as you were to install it in later versions of the kit, sort of flying between the PC board and the on-off switch with a little bit of sleeving in it. And here's a fuse F1 in later versions of the manuals as a schematic. But it was really not the way to go. So since this has no fuse at all, I think we'll put a terminal strip and a proper fuse holder, AC fuse holder, down here where there's plenty of room, and wire all of the AC stuff, the switch, the power light, the transformer, and the fuse into that directly, and properly insulate it, and therefore get everything off of the circuit board to properly insulate the secondary, the low voltage side of the power supply from the mains side of the power supply. Also, as is not the case here, it's good practice to have the hot side of the line cord first go into a fuse and nothing else. In other words, you don't want the hot side going into a switch and then into a fuse, or nevertheless, certainly you don't want the hot side going into a PC board with all sorts of traces, and then eventually into the switch with or without a fuse. You want the hot side of the AC line to go straight into the fuse first and then take it from there. So we'll be doing that too. So in order to do a recap, or never mind a rewire, you really have to take the whole thing out of its case because there's really no access. And when you originally build the thing, it goes in and then things get wired to it. So you have to unwire things before you can get it out. So here it is in partial disassembly. The controls, or the two potentiometer nuts are gone, so those are loose. Notice the power switch is unscrewed. I can't unscrew the banana jacks because they have to be unscrewed from the inside, which means I can't get rid of them or undo them until the whole thing is out. So I'm going to have to probably just clip their wires, and I'll be rewiring that anyway. On this side, this little terminal strip here is loose now, but there's no way to feed it back through its hole. So I'm going to have to clip its wires just to get it out, and then rewire it again back into the board when things go back together. I don't have to desolder or undo the power transistor, the pass transistor socket. This is a TO3 NPN pass transistor. You do have to unscrew the little cover and pop the transistor out of its socket, but then the socket comes loose, and that's not a problem. The power indicator here, the neon power light, actually will come out of its little lens, so you can leave it. I can see it will come out if you're very gentle when you pull the board out, because these leads are, of course, very fragile. So they don't have to be unsoldered. The thing will come out from its lens when I pull the board out. Finally, and annoyingly, the line cord grommet uses one of these infuriating line cord strain reliefs. They work, but they're infuriating. The best I can tell you is that a small vice grip is your friend with these things, especially to get them out. And they come out very quickly if you have a vice grip. But it means, as a practical matter, I have to unsolder the line cord, which I've got to do anyway, so I might just clip it and then clean up later. So that's what, and of course, I'm going to have to unscrew the power transformer and the circuit board hold down bracket here, which I've already unscrewed, and then unscrew the power transformer hold down nut screws, which are here, because unless I take out the secondary wires, I clip all the secondary wires, which I'd rather not do. I'd like to keep them in place. The power transformer and the circuit board have to come out very gently as as a single unit. And I'm not going to show you that on camera because I only have two hands and it's really scary, and I might mess it up, and I'd be ashamed of that. But nevertheless, we'll be right back. But before then, I thought, here's the pass transistor. It's a Heathkit 417162. I believe it's equivalent to a 2N3055, which is one of the most common power transistors that ever existed. But I will be checking this on a proper transistor tester because on my other vintage unit, the 50-year-old power transistor's gain was not really what it should have been. So I don't know if it's age or whatever. Maybe it was just manufactured with lower gain. I don't know. So of course this one does work, but I might replace it with a modern 3055 because these are still made because they still need them for replacement purposes. So we'll see. Anyway, just cute. This is obviously an original Heathkit part because it has the original Heathkit part number. So here's the beauty shot of all the parts, at least that had to be disassembled in order to get the circuit board and transformer out to have better access to it. A couple of things, you'll recognize all of these parts. I didn't take the binding posts off the chassis because it's not necessary to do so. And apart from that, there's a little lens and its clip for the neon light. The neon light is still attached to the board as you want it to be. So is the power switch. So is this back panel terminal strip and the power transistor and its socket. So those are just flying off in space because there's no cabinet. And so the next thing is we're going to be turning it on. But at least here's, so far, the partial disassembly. So here are the guts of the IP-18 power supply outside of its case. As I mentioned, it is a kind of a bear to remove from the case because you do have to desolder a couple of things. As I mentioned, things I didn't have to desolder were the power switch here, the neon lamp power on light because it just slips right out of its little lens, which is kind of nice. Although it's incredibly fragile, these neon lamp wires that are going into the circuit board are very fragile, as you probably know. I did have to unsolder the rear terminal strip because there was no way of getting it out without disconnecting the three wires, so I just quickly tacked those back where they were. The transistor is temporarily back in its socket with this screw in to maintain the case to, well, the collector connection is thanks to this screw, so that has to be there. And normally this transistor is insulated from the back. The collector case is insulated from the back panel. So you want to make sure that on your back panel you don't lose the insulating, the mica insulator, which is really thin, sort of oblong, TO3 shaped piece of mica. I'm probably going to be replacing that with a better heat sink insulator combo. In fact, these are the TO3 thermal conductive insulators that I'll be using. I have to order these from NT Ports Direct because as you'll see later, I ordered some of the other semiconductors there as well. The line cord is of course gone, and there's just a white and black wire, the hot and neutral, which are going into the circuit board, and they're going into a source of AC here, the Cliff Quick Test. I'm just going to focus in a little bit on, why I want to remove all primary AC from the circuit board, because from the line cord, we go into these traces here, which go to the power switch here, and then it comes all the way back here, then it goes to the primary of the transformer, and across that also is the neon indicator. There's also jumpers here on the front of the board to select whether you want to wire it for 110 or 240 volts. You probably can't see it very well here, but that's typical Heathkit. You can wire there's the primary, actually, let's see which side. Yeah, this is the primary side. There's four primary wires to the transformer, and you wire them, and you wire two in parallel for 110, and you wire them in series, the two coils in series for 220. I'm never going to be using this on 220 or 240 mains. So when I'll be taking AC off of this board and putting it all on proper terminals and insulated, I'll just more or less permanently set it to 110. But so you can see these traces, probably why I want to get all hints of AC off of the board. The other thing that's on the board is the dropping resistor for the neon bulb, and that's going to come off the board too and just be wired into the terminal strip. So that's what it looks like. I guess it's time to turn it on, since everything here is now reconnected as if it were in the case and ready to go. The power switch is on, but the AC is disconnected, so now the moment of truth. And I'm doing this just to make sure that I didn't mess anything up as I was wrestling the whole mess out of the case, because the transformer and the circuit board all have to come out as a unit unless you want to disconnect all the transformer wires, which you don't want to do. So here we go. Contact. And oh, good, the neon bulb lights up, and I have the multimeter across what would normally be going to the binding posts on the front, so the DC output of this. And right now, the voltage pot is set to its minimum, the current pot is set to its maximum, and I have a little less than 1 volt. So again, this power supply is rated for 1 to 15 volts, so it cannot go down unless you turn it off. It cannot go down to 0 volts, and so the minimum voltage, and I've seen this on other instances of this, is about 0.6 of a volt. And as I move the voltage pot up, 3 volts, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and that tops out. And so although it's rated 1 to 15 volts, the top end is now 16, it's 16.7 volts. So it gives you a little more wiggle room to play with, and that's fine. You can, of course, dial it down to 15 volts if you want. Pot needs probably a little cleaning. It looks like it sounds a little scratchy. The current limit does have an effect at its low end if you turn it all the way down with no load. Ideally, it would do nothing with no load, but it does limit and go down to about 14 volts. It causes the output to go down about 14 volts, no load, but that's fine. But of course, the current limit. So the current limit at pot is doing something. I suspect it is working fine, although I don't really plan on putting a load in this just to test it. It all appears to be fine and working just like other examples of this are. So now we're going to be, now we have unfettered access to the circuit board. We can do a little bit of recapping, undo the primary of the transformer, and get the neon bulb off of there, get the power switch off the main circuit board, get the primary connections off the circuit board, add a fuse. There's no fuse here yet because never was built with this particular instance. Was an early model without the Heathkit provided fuse, which would come later, and would be simply wired in series here with one of the power switch terminals. Brilliant. And we'll be cleaning up this resistor mess, adding a terminal strip. Again, we're going to try and make this look a little bit more safe and a little bit more modern, so it can continue to serve for many, many years. So here's the full frontal view of the circuit board since it's out. So what's interesting about this is it appears to me that this capacitor which is the main input side capacitor to the power supply. It's 2500 at something 50 volts or something, and this one here are very likely original, and so is this little guy here. But these two were not, because this is the wrong voltage value. This is supposed to be a 50 at 60 volts, but it's a 50 at 50. It's not a big deal, and it probably still works fine, but that's how I can tell that this, and then this, of course, was not an original Heathkit. It's not modern by any stretch, but it dates after the original, the 60s and 70s. And I didn't have any reason to believe that any of these capacitors are actually bad, although I haven't tested them yet. Again, the power supply seems to work fine, although I did not put its output on the scope to see what kind of ripple it has. But now that I have this thing out, I notice something here, some crustage on this filter cap. This is a main input filter cap. There's these little tiny, you can't see them, but there's like 1, 2, 3, 4 little vent holes, I guess, or something, and this one's exuding some crud. So I suspect, even if this capacitor is quote good quote, it's it's past its prime. So it will be replaced by something more modern, and no doubt smaller, and no doubt radial lead instead of axial lead, because axial lead capacitors are becoming virtually impossible to find anymore. An axial capacitor is one where the leads come out of each end. A radial capacitor is where both leads come out of the same end, because they're designed to be mounted on PC boards. No one uses axial lead capacitors anymore because, well, these were used back in the days when you were building radios with point-to-point, wiring with no circuit board at all. And then circuit boards came along, and of course Heathkit had huge stocks, and at the time axial leads were still being made in huge quantities, so they put axial leads on the circuit board, so the capacitor is lying down instead of standing up. But now all capacitors are pretty much radial lead, and so that doesn't make them any worse. You just have to extend the lead. Anyway, we'll see that when I finish recapping this. Apart from that capacitor, the others look okay, but I'll probably change them, especially the two originals here. They might as well go, because why not, since I have this thing apart. Other things of interest, one of the transistors, which is, I believe, Q2, is this guy. It's the first time I've seen this guy on this Heathkit, this model of Heathkit. These sort of domed capacitors of yore, instead of a TO92 package or something similar. So this is another reason why I believe that this was one of the original IP-18 kits. And this down here is the constant current, the FET that's being used as a constant current source, Q1. It appears to be working fine. Then there are a couple of transistors here, Q4, and I forget which is the other one, Q5. These are 2N3393s. These are interesting because you got to be careful. These are not emitter base collector. These are emitter collector base. Yeah. So you just want to be careful if you're substituting. Anyway, this is the glamour shot for the power supply in its working state, reconstituted, but outside of its case. And just for completeness' sake, here is the flip side, the trace side of the PCB. Nothing much to see here. Whoever built this, presumably 50 years ago, did a decent job. I don't see any obvious cold solder joints. And again, the kit works. And although he didn't clean all the flux off, I've seen far worse. And again, a couple of things here which are annoying. The AC power switch is wired into the back side of the PC board here, or these traces where AC is running around, really close to the DC out, out second front side of the power, back side of the power supply, and then the AC pilot light is similarly wired in. All of that's going to go. All of the AC mains is going to be off of this PC board and back into the chassis where it belongs. But apart from that, not much to see here. It all looks reasonably good. Honestly, I don't know how anyone can go through life without one of these. Expensive, but worth every penny. So the IP-18 has 5 capacitors in the whole product. All 5 are electrolytic. On the left are the ones that I removed from the board and the chassis, and on the right are their modern replacements, which I believe are all from Mauser. No, not sponsored. Originally, when I first cracked the box open, I thought maybe someone had been inside in this thing and had partially recapped it. In particular, this guy, because it just didn't look like any of the others. So I wonder, okay, maybe someone had been in here, and maybe even this guy. But then I looked at the original caps from my, and also because when I looked at the original caps from my other IP-18, the one with the meters on it, this was the equivalent cap pulled out of it, which is strange because it looks older, but it's smaller, and it's exactly the same rating, 250 at 50 volts, as, it's really strange. By the way, the replacements are all very close. The 250s are 270s, the 50s are 47s, and so forth. In fact, I believe this is the only one that is slightly underrated. This is actually, what is it? This is actually 270 at 35. So it's a little underrated voltage-wise, but given where it is in the circuit, that's not going to be a problem because it's not going to see 35 volts. It should see about 25 volts. So I would have liked to have a slightly beefier one, but that's all I could find at a reasonable price at that instant. So that'll work fine. Finally, and by the way, the other reason I know that if these were replacements or original, I know they're old because they show their positives, their positive sides, not their negative sides. All modern capacitors, for some reasons, label their negative leads, not their positive ones. And finally, you notice that all of the replacements are radial leads because, well, that's just the way it is these days. There are really no more axial lead capacitors available, electrolytics, that are anywhere near affordable. So radial it is now. So these are the ones that are going to be going in. Well, making some progress here. I tested in circuit all of the resistors on the board, and all of the little resistors, the half watters, were high. They had drifted up, and so I pulled the 1800 one off just for the sake of it, and measured it out of circuit, and it's measuring 2100 ohms instead of 1800 ohms. That's something like 17%. And this is a 10% resistor, so yeah, it's drifting up and out of tolerance. So I'm just going to remove all the half-watt resistors and basically replace them with metal films or whatever I happen to have. The power resistor is spot on. The 3300 1 watt is spot on, and the 0.51, I should say, 0.51 ohm 2 watt resistor seems close enough. I'm hoping not to replace him because I'd have to order that. I don't really want to. So we should be good. And even since I had to pull it out anyway, that flying 1K resistor, which was literally flying between the board and the back panel connector terminal strip, that 1K resistor, which is 10%, is 1.17. So yeah, that's 17% off as well. So I don't know. I'll probably take a look, and I have a feeling that all the half waters have drifted 17% up, but it looks like they're all going to go. And this is R8, which is a 27K. This is the neon pilot light dropping resistor on the AC side. It used to be here. It has to come out because it's on the AC side, and I'm putting all the AC stuff, taking all of that off the PC board, and it's going to be chassis mounted. And it's measuring 31.66K, again, should be 27K. So why don't we do this? 31.66 minus what it should be, 27K, is 4.66K. Difference divided by 27K again. And what do you know? 17%. Here's the IP-18 PC board with basically all of the parts that are going to be removed, as well as the transformer primary parts and all the things that have to do with line voltage AC, which will not return to this board. But as you see, there's the power resistors and the semiconductors all tested pretty good. Of course, the potentiometers did as well. So here are the electrolytics with their leads formed. Obviously, these are radial electrolytics, and they had their leads formed and put some tubing on them to insulate the negative side, so they'll fit in the holes on the PC board, as well as the two resistors, the two half-watt resistors that are being replaced. Here's a schematic of the IP-18. This particular schematic I happened to find on the interwebs. It is not in any of the 3 different revs of the official IP-18 Heathkit manual that I own. So it's out there if you search for it. Everything on this schematic that is handwritten is my handwriting. Everything else came from the schematic itself. I like this one because it's redrawn from the original manual, plus there are a couple of extra parts, specifically D6 and D7, which I wrote in, which were not in the original kit build. We'll go over some of the things in this schematic quickly. You'll notice a whole lot of rectifiers that I wrote in. So these are the original Heathkit numbers, such as 417 and 118 here. These are the Heathkit part numbers that are in the original manual, and were for the most part supplied as part of the original kit back in the 70s. The other numbers are substitutes, either official ones, which are also in the official Heathkit manual, or the ones that are on this schematic, which are the printed ones, or other substitutes which I had to find online because I wanted to make sure that I could replace all the semiconductors and that they would work. Everything, each part that has a little dot in front of it, such as here, here, and here, that's the actual part that I wound up installing in this refurbished IP-18. And it all works fine. The 2 things of note I think that I'll mention here are, first of all, the addition from on top of the original manual that this particular schematic redrawer added were these 2 diodes, 1N4002s, which I call D6 and D7 for no other reason that those are unused. They were not particularly labeled anywhere else. But they are labeled as 1N4002, so they're just being used as protection diodes. In the case of my D6 here, this diode is reverse biased and is designed to protect against, so let's say the power supply is turned off, and let's say someone decides to feed voltage into the output of the IP-18, and let's say someone decides to reverse it, so put positive voltage here and negative voltage here of God knows what voltage. Well, that's going to cause some problems. First of all, you'll notice this filter cap here is polarized, so that's the most, I guess, closest problem. But then also that's going to start affecting the PN junctions between on some of these semiconductors and could harm them. So anyway, this diode would simply dump that current if you choose to backfeed the power supply with reverse voltage. On the other hand, the other thing you do is backfeed the power supply that's turned off with positive voltage. So let's say you connect this supply in parallel with another supply. You turn this one off, you leave the other one on. That's gonna have mean that this side is going to be more positively biased than this side, and that's going to be a problem on a few fronts, in particular for the pass transistor, possibly, and possibly other components as well. So this diode will simply bypass that and basically protect the pass transistor. But normally both these diodes are when you're using the power supply properly, both these diodes are reverse biased and therefore not really in circuit. The other thing I want to mention is this diode here, the 1N191 or Heathkit 5626. This is clearly a germanium diode. Before we go any further, let's talk a little bit about all the different diodes that I found as substitutes for this and their forward voltages. We'll be right back. This is the original little glass diode for the IP-18 diode D5, which per Heathkit is a 56-26, or it can also be from Heathkit a 1N191. This is the original diode from the early 70s when the kit was built. And actually the diode works fine. Its forward voltage is about a quarter volt. This is the NTE 109, and its forward voltage is a little bit above half a volt. Here's a 1N4002. This is, of course, a silicon jelly bean rectifier diode, and its forward voltage is a little more than half a volt. This is a 1N5817 diode. It's actually a Schottky diode, and as you would expect of a Schottky diode, its forward voltage is only about 0.2 of a volt. So looking back now, according to the manual's circuit description, the purpose of D5 here is to protect Q4 against reverse voltage being applied to the plus and minus external programming terminals, which you could do if you again, if the power supply is off and you reverse bias this, you could make a hash of Q4, and so this is designed to protect that. In addition, I asked myself why 1N191 is clearly a germanium diode. Well, let me put it this way: 5626, and presumably the 191 is definitely a germanium diode because I measured it, and you saw the voltage drop, and that's good because the way this circuit works is, let's say the more you set the voltage low, which means let's say you move the pot up here closest to the positive rail, that's going to feed more positive to the base of this. This will conduct more, Q4 will conduct more, which will tend to suck current away from this node here, which will have the effect of slowly turning off more and more the pass transistor, which is really set up as a Darlington pair, and therefore the output voltage will go down. That's really how the power supply works in terms of voltage adjustment. Now, the voltage you select with voltage control is passing through this diode, so there is a diode drop here. The diode really doesn't do much because there's not a whole lot of current going through the base emitter. But what it means is, let's say you wanted to select minimal voltage. So let's say you did turn this all the way down, so you maxed out the positive voltage here. The more diode drop you have here, the less effective that becomes in terms of lowering the voltage, because that's going to reduce the conductivity of Q4, which will suck less current away from the pass transistor, which will let more voltage out. I tried substituting this, of course, and I found that the difference between the original diode, which had, I believe, a quarter volt voltage drop, being germanium. So I put in the NTE 109, which NTE specs as a direct replacement, and I measured its forward voltage, which is about half a volt. And the net effect of this is minimal. All it means is that if I dial the voltage all the way down, I can get, rather than get the minimum voltage out here at say 0.6, 0.7 volts, which you could do if you put the germanium one in, I could get it down to 1 volt only, because again, it was less effective at turning on Q4 to suck current out of the pass transistor. It's not a big deal, of course, because the power supply overall is only rated from 1 volt to 15 volts. It isn't really rated from 0.6 or 0.7 volts to 15. It's rated at 1 volt to 15. So if I can dial it all the way down and I get exactly 1 volt out here, which is what happened, great. So the other thing I noticed is the NT 109 and even the 4002 all have the same voltage drop. So I'm not even sure that the substitute NTE 109 is really a germanium diode. I don't think it is. I think they spec it as a substitute simply because it's okay as a small signal diode, but it's if you look at the spec sheet for the NTE 109, its its max forward voltage is 1 volt. So it's this one's doing very well at half a volt, and it's of course nowhere near a quarter volt. So there you have it. So any of these will work fine. The worst that can happen is if you have a high enough forward voltage, you won't be able to dial the power supply down to the 1 volt minimum as you want to. And I showed a couple of other forward voltage drops. The 1N 4002 is half a volt, so presumably I could substitute one of those in and it would work just as well. Frankly, I suspect they picked a germanium diode here because they wanted something with a fairly low voltage drop. And back in the late 60s, 70s, well, that's what you got. You got a germanium diode. These days, you'd probably put in a Schottky diode, and that's why I also show a typical Schottky diode's forward voltage, which is 0.18, 0.2 of a volt or something. The only downside I could think to using a Schottky diode here would be, first of all, it's really unnecessary, as we found, and secondly, the downside is, well, there's presumably a little bit of tiny more leakage current. It'll, in the reverse biased, it would leak about up to 1 milliamp, whereas a normal silicon diode will leak far less than that. But again, that would only happen if you actually reverse biased this the wrong way. So that's the things of note in this schematic. This is the completed IP-18 circuit board with all of the half-watt resistors replaced because they had pretty much all drifted upwards. Although, as I mentioned, the larger 2-watt and the 5-watt resistors were spot on, so go figure. I also chose, of course, to replace all the electrolytics with obviously radial leads because that's what one can get. And so bent their negatives back with some heat shrink tubing. Let's see. Oh, I also replaced all of the semiconductors, not because any of them really needed to be replaced, but I wanted to make sure that the substitutes that I put in and that I was going to put into maybe another IP-18 would actually work and not affect the operations. I just wanted to make sure that all of the substitute I picked were valid. And I'll list those on the annotated schematic, which I'll put up elsewhere in the video. Apart from that, the only thing I added was also in that schematic was a diode here, which you may or may not be able to see, which is reverse biased. Basically, it's the reverse bias diode across the output, and that's to protect the power supply against applied reverse voltage. And you can't see it here, but on the traces joining the collector and emitter of the pass transistors is also a reverse bias diode to protect against reverse overvoltage applied back into the power supply. So this is the finished board, and we'll be mounting it back in the IP-18. So we know that our power supply can deliver 15 volts, in fact up to 17 volts, and with a 220 ohm resistor as a load, it did so with double digits of milliamperes, and that was good, and all was good, and the current limiting worked. But now we want to make sure that our power supply can deliver its full rated half an amp or 500 milliamps at 15 volts, which is actually what it's rated at. And to do that, we need a more appropriate load. So we have here a load across a 33 ohm 1 watt resistor. Yes, and you'll see why in a minute. And we're going to do two things. We're going to make sure that this can deliver half an amp, and we're also going to release some magic smoke, because I'm told that electronics videos which have magic smoke released actually generate more likes. So we'll see about that. So without further ado, the power supply is actually on right now, and it's delivering 15 volts, but there is no current because I've interrupted the current flow. So I have the current control cranked up, and voltage is set to 15 volts. And so without current limiting and 15 volts, let's plug this in and see what happens. And yeah, as expected, we have just shy of half an amp, so 480 milliamps, and going up. But of course, if you do the math, that's about 7 watts of power being dissipated on the load. And this is only a 1 watt, if that, or a half watt resistor. Oh my goodness, magic smoke. I don't actually want to run this forever, because this pass transistor, actually it's not getting warm at all. Is it? Nope. Because normally it's mounted on the rear panel as a heatsink, but it isn't. So, oh my goodness, our resistor is basically done. Yeah. Well, there was because it lost all of its magic smoke. There is no more magic smoke left in this resistor. And so it is now pulling only 155 milliamps, and it is smelling terrible. But we've proven that at least for some period of time, we can draw 500 milliamps at 15 volts from the power supply, and then the power supply doesn't really care at all, and that is good. So let's turn it off. So at 15 volts, I said we're drawing 69 milliamps. That's about right. If this were really 220 ohms, and I think it's 217 when I measured it, we're actually drawing a little less than that, 68 milliamps. But anyway, so that's correct. And we can actually test the current limiting. I don't want to leave this on too long, because this is drawing 1 watt, and it looks like a not quite 2 watt, 1 watt resistor. So let me dial this down to, let's say, 10 volts. Let me turn the current all the way up. It is. Let's dial it down to 10 volts. And this is actually the procedure, one of the procedures the manual suggests. So we're going 10 volts, and at full current we're drawing 46 milliamps, which is about right. Now I'm going to reduce the current slowly, the current limit, and slowly nothing's going to change until all of a sudden the voltage is going to go down. And so is the current. Keep going, almost there. Oh, there we go. Just there. So let me pump it right. Let me put the current limit right back up to the edge, or the knee. There we go. 10 volts. Again, just so right there. So 10 volts, 46 milliamps, but it is limited now to 46 milliamps. So if I try to up the voltage, notice it really isn't letting me. I can reduce the voltage, but the voltage is going to be, we're going to be stuck at 48, let's say call it 50 milliamps, but I drift a little, but I can't go past 10 or 11 volts. So it is, the current limiting is working. Let me go back to 10 volts, more or less, hey, on the money. And, yep, and right, still, yep, right there. I was still right where it should be, so back there. So that's the knee, 45 milliamps. And again, if I up the current limit all the way to the top, I can up the voltage further than 10 all the way to the rated 15. If I go down to the 17, or if I go down to 15 volts, roughly, yeah, close enough. Drop the current a bit, set the current limiting low, and there we go, right there. Limiting it to 69. So anyway, this proves that voltage adjustment works, voltage output all works, and the current limiting function works as expected. If you recall, the kit has a 1,000 ohm, 1K half-watt resistor sort of flying from the PC board to this rear panel terminal strip. I decided to fix that in re-engineer that better in this form, to add a little tiny terminal to the rear to accommodate that the new 1K resistor. And here's what I believe is a 25 mic cap, which bridges terminals 1 and 3 normally. So I put it down there with some Teflon insulation. So that's sitting there. That's 1K resistor. And then instead of 2 leads and a resistor flying off to the PC board, there's 3 leads. And I decided to give them different colors so that when I can identify them on the PC board, I know exactly where they're coming from. And you'll see this as I do this on the other parts that fit on the front panel as well. Here's the pass transistor, the TO3 transistor socket, which normally will mount on the rear panel of the IP-18, and again I gave it new color-coded wires so that I could easily identify which is going which on the PC board. And the power switch, which of course will go on the front panel, and again be wired to the chassis, not to the PC board. A new little NE2 neon lamp for the front panel lens. The resistor, I put a resistor in series with it and shrunk the whole thing in heat shrink tubing. And again, this will not be connected to the PC board, but will go to a terminal strip for all things AC onto the chassis. New fuse holder, ditto. This is new. And rather than being a flying fuse as it is on some of the Heathkits, this will be a chassis mount fuse holder. And here's the completed and restored IP-18 chassis with all of the AC side wiring completed and the DC output side wiring, the binding posts here and the secondary of the power transformer here. Both of these are going to be soldered to the PC board. That's really the only things which are going back onto the PC boards. All the AC components, namely the power switch, the neon light, which I redid with a resistor, and then a new fuse, and then the primary side winding onto a terminal strip, and of course the line cord and the ground and everything else. That's now on the chassis rather than on the PC board. I just wanted to get all the AC stuff away from that PC board and off of its traces. That's basically it. So now all we have to do is mount the PC board back into the chassis, and we'll have a working IP-18 even better than new. And finally, here's the IP-18 completed. the complete rebuild. Works. Everything's installed. Works fine. Turns on. Checked it. Passes all the tests. If we look inside, basically, as I mentioned, all the AC stuff has been removed from the circuit board. And you'll notice there's a little bit cleaner wiring, although I've left a fair amount of slack in the wiring. I can actually remove the circuit board now without removing the transformer and all the other stuff, and without having to desolder absolutely everything except perhaps the secondary wires here. But everything else is long enough. And if we look at the rear panel, here's the terminal strip, which has the 1K resistor, so it's no longer flying into the PC board. Transistor socket. Here's all the AC stuff. There's a fuse holder that you see, that sort of yellow thing with a little green tab on it. Terminal strip, which holds all the primary side transformer leads and the line cord and connections to the power switch, as well as the neon lamp. So that's basically what it looks like inside. It's a bit cleaner than it was. Again, new caps, all new resistors except for a couple, and all new semiconductors. So that's our IP-18. So it's been a few days now since the last clip, and I had some thoughts that I wanted to tack on to the video. I guess the first thought is, this arrangement, which was designed to mount the 1K resistor, which used to be flying between this terminal and the PC board. Of course, this works. I'm not sure I'm entirely happy with it from an aesthetic point of view. At the very least, I should cut off this ground tang, which serves no purpose because it's part of the mounting thing for this, what's now a 2-terminal strip, which is soon to be a 1-terminal strip. In hindsight, I think I could have probably not without too much difficulty, found a way to do a little bit of cutting and hacking and drilling on the board, so I could actually mount the 1K resistor on the PC board, and then simply have the wire, which in this case is yellow, go straight to this terminal where it was intended to be, where the resistor originally would have landed. So I probably could find a way to make the 1K resistor PC mounted, and eliminate the need for this little power strip. The other thing I did, which you may have noticed, which I don't regret at all, is I'm using stranded hookup wire, color-coded stranded hookup wire. Now, the Heathkit purists will bemoan the fact that I'm not using, solid 24 gauge blue hookup wire. I just don't care for it. Plus, it tends to, I don't know, it tends to break off if you wiggle it too much. I mean, it fatigues more easily. I don't know. I just don't like Heathkit's solid blue hookup wire. So, it's my kit, so I decided to use stranded, and it obviously works just as well. And the color coding really, really helps. If you can't remember which wire goes to which spot on the PC board, now you don't have to trace it out. You can just look. In addition, I did clean the 2 pots with some deoxit, and now they are buttery smooth. So I'm really happy with the way they feel. No more scratchiness. Very easy to get to that exact voltage you want. So that was always a good thing to do on 50-year-old potentiometers. So this is a still from the video, and I just want you to take a look at the part number 85-259-1. So it turns out I have another IP-18 that I've totally disassembled, and I just noticed something interesting on its circuit board. Notice its circuit board part number 851642-1. So I'm going to guess that this PC board is actually a newer rev in some way than the old one, than the one I just built. And I looked really carefully at the silk screening and drilling of this one versus the screenshot I took of the other one, which is now built, of course. and they're absolutely identical, essentially. So I think whatever they did, it really looks like they reused the front silk screen. Let's take a look at the backs. Here, of course, is a still again from the video. This is the back of the one I built, which I believe is the older Rev. Again, 85259. And in the video, of course, I was ranting about the size of some of these AC traces running around. Let's take a look at the rear of the trace side of the newer PCB, or what I think is the newer one. And here's the foil side of the newer Rev of the the IP-18 PCB. And you'll notice something interesting. First of all, there's damage here. These traces lifted, but that's not a big deal because this is actually where the power switch goes from here to here. Notice, though, the significantly increased separation between the AC traces, which are basically these two, which go to the power switch, the primary side of the transformer. Everything from this trace down to this trace is AC. And so they've actually significantly increased the separation. And I didn't notice this until after I did the video. Nevertheless, if I were going to rebuild this unit as well, and maybe I will, I would again not mount damage would be irrelevant, because I wouldn't mount the power switch or connect it or the neon bulb, which is has to do with these traces here. I wouldn't connect it or the neon bulb to the PC board anyway. But it looks like someone at Heathkit said, those traces really should be separated more, and so let's redraw the backside of the PCB, and they did. I don't know if this is a date code, but if it's 6/18/1974, I suppose that's plausible, because that would be towards the latter half of the production life of the power supply.